Okay, so this is part 12.2, and I will call it determinants part 2. So, okay. So here our goal is to prove the determinant of a product of two matrices is product of determinants, and I will do it by proving a more fundamental theorem, more abstract theorem. Let me state it. So, theorem. Okay, so let V be a vector space with bases E1 up to En. So consider a vector space with bases E1 up to En, and then there exists a unique function which I will call function phi, and then this function is a function which takes a product of n copies of our vector space to F. So again, so our function has n arguments, each of them is a vector, such that so I will give an example in a second, but before that, so such that the following properties hold. So first is that so this is called polylinearity. So what it means that if you take V of a tuple of vectors V1 up to Vn, and somewhere inside there is vector Vi, and Vi is presented as a sum of two vectors Vi prime plus Vi2 prime, then the sum equals to phi of V1 to the Vi minus 1 are the same, but then Vi is substituted with Vi prime, everything else is the same, plus phi of the same thing, but now we have Vi2 prime, Vi plus 1, and so on, Vn. So if you decompose one vector as a sum, then the function is a sum of the functions where we take Vi prime instead of Vi and Vi2 prime instead of Vi. So this is the first property, and this is true for any I from 1 to n. So second property is called phi is antisymmetric. So what it means that for every I not equal to j, so if you take phi of V1 to the Vi to the Vj Vn, that equals to minus phi, and then you take the same guys, except you put Vj in the position Vi and Vi in the position Vj. So you just exchange these two guys with each other and everything else stays the same. So this is called phi is antisymmetric. And the third property is the most simple one, and it's called normalization. And this is just says that if you plug in E1 up to En, this is just 0. This is 1. So if you put just first two properties as your axioms for such functions, then actually there will be a lot of them, but all of them will be one, each is rescaling of another, and so the interesting one is just 1. And of course, this function is nothing but determinant. So let me start proving it, and I will start with existence. And existence just is easy because this is just determinant. So and for that, so let's consider a collection of vectors v1 up to vn, and then take phi being equal to determinant of a matrix where v1 up to vn are just column vectors. So then part 1 is the one which I described in the previous part of the lecture, where I take one of the vectors and write them down as a sum of 2. And I guess I did it with rows, but the same is true for columns. And the fact that it is antisymmetric, it is exactly what the first column operation tells you. So 1 from last lecture, 2 is because this is just column operation number 3. Just exchanging 2 columns flips the sign of the determinant. And finally 3 is just because if you take this determinant of a collection of vectors e1 up to en, of course by that I mean I just need to write down these vectors in this basis, and this will be just determinant of the identity matrix. And this is 1, as we discussed again in the previous lecture. So that's why existence is proven, and this function is determinant function. And interesting question is why it's actually unique. And for that, let's just see where it comes from. So let's suppose that our vector vi equals 2, and then I will just write down in the usual notation the ith column. So ith column is a1i up to ani. So of course this equals to a1i e1 plus t plus ani en. And then we can just compute this phi of v1 up to vn, and so we can just compute it by opening brackets. So let's just do that. So this equals to the sum, and let's apply this formula and the first property, polylinearity, for one second. There is another. So one property is that this is linear when you write down a vector as a sum, but also there is another one which says that phi of v1 to the lambda vi vn is lambda times phi of v1 vn. So if you rescale one of the vectors, this phi will multiply by lambda. So basically you can think of it as that if you just look at one argument is varying whereas others are fixed, then this phi is just a linear map from v to f. So that's why it's called polylinearity. So let's apply this last property, these two properties to vn, and thus we will get some phi of v1 up to vn minus 1, and then ei times the coefficients of ei, which is just for vector vn is a ni. So then we can apply the same rules and sum from I equal 1 to n. Let me call this in. So then I can write down each of them as a sum where I have vn minus 1 presented using this formula. And so eventually I will get a sum when I open all the brackets from I1 and so on up to In from 1 to n, phi of ei1 up to ein times a 1i1 an in. So this is the formula which I got, and of course it starts to look a little bit like determinant, because in determinant we have firstly in the determinant we have, so here we have n power n monomials, and in determinant we have n factorial, which is much less, and also we should do something with this phi, guys. So, but I will prove in a second that this is exactly determinant. Okay, So for this, we prove the following little fact. So if two of the vectors v1 and so on vn are equal, then phi of v1 vn equals to 0. So this is just because if two of them are equal, then we can exchange them and it flips the sign and simultaneously doesn't change anything. So to be honest, if your field has the properties that 2 there equals to 0, like in F2 for instance, then probably you need to add this requirement that this thing vanishes for 2 equal vectors. But that's just a little correction. So why this is the case again? So we flip these two vectors, the function changes sign and simultaneously doesn't change because they are equal. And so phi of ei1 up to ein equals to 0 if 2 of the indices coincide. So a lot of terms here vanish. If just 2 of this out of these indices coincide, then they vanish. So if all I1 up to In are different, we can consider a permutation. One goes to I1 and n goes to In. So this is a permutation because they are all different. So we have a bijection from a set injection from a set of n elements to itself, and since injective map from a set to itself, which is finite, is also surjective and also bijective, then this is a permutation. So and then phi of ei1 and so on ein equals sine, let's call it sigma, sine of sigma times phi of e1 en, which is just sine of sigma. So, and why this is the case? Because we know that when we exchange two vectors, then our phi is multiplied on -1. So when we do transposition to them, we pick up -1 sign. And so if we do even number of transpositions to put them in the order e1 up to en, then the function won't change. And if you do odd number of transpositions, it will change sign. So that's why it equals to sine of sigma times phi of this vectors ei1 up to ein going in the order from 1 to n. But then we normalize phi so that phi of e1 up to n equals to 1. So that's why it's just sine of sigma. And then, of course, the sum is nothing but, so this is just a sum over all permutations sigma and Sn, because, so these terms vanish for when two indices coincide. So only these terms don't vanish, and then we have the sine of sigma, so this -1 power sigma. And then we have here a1, and I1 is sigma of 1. So sigma of 1 up to an sigma of n, which is, of course, just determinant of this collection of vectors v1 up to vn. So that's why it's unique. We just computed it, and this is exactly the determinant. Okay, so determinant can be abstractly characterized as this nice function, which takes a bunch of vectors and gives you an element of the field, and has a property that it is linear in each vector as a variable, and it equals to 1 if you just plug in the basis, and also it changes the sign when you flip two vectors. So this is the theorem, and as you see, it's not very hard. It is just this bracket opening plus the properties of determinant we know. but it has a remarkable corollary, and this is the main statement of this lecture. So next I will prove that determinant of a product of two matrices is product of determinants. Okay, so now we prove the main result of this lecture. So theorem. So let's suppose we have a pair of matrices A and B. Then determinant of A times B is determinant of A, determinant of B. So determinant is multiplicative. This is the most important fact. This is absolutely remarkable. And if you think about it, if you just try to prove it opening brackets, it will be terrible, very complicated, huge proof. But I will do a proof which does not require any computations at all and basically uses the idea of the previous theorem. So proof. Okay, so let's look at a vector space V, which is just Fn, and then so we can look at E1 up to En some basis. And then so we know that determinant of vectors V1 up to Vn. So this is a function, unique function satisfying properties 1 up to 3 from previous theorem. But now let me construct another function like that. So consider the following function. Sorry, 1 second. So yeah, consider the following function. Consider the function A times V1, A times Vn, and then determinant. And so let's suppose it is yeah. So this is some function psi of E1 up to En. And then my claim is that, so this determinant of AV1 up to AVN is just determinant of A times determinant of V1 Vn. Okay, so there are two cases. So yeah, and by the way, A of V1 is of course some linear map applied to the vector V1, the linear map corresponding to A, if you think of a matrix acting on F power n. So proof. So there are two cases. So case 1 is, sorry, okay, case 1. So case 1 is determinant of A is equal to 0. So then, as we know, determinant of A is equal to 0 means that A is not an isomorphism. And then, of course, what it means is that image of A is not the whole space V. And then, of course, AV1 up to AVN are linear dependent. Just because they lie in the image, and the image is not the whole space, so it has dimension less than n, so we cannot find n linearly independent vectors there. But then determinant of AV1 up to AVN is equal to 0 as well, just because these are n linearly dependent vectors. So this was easy. And then there is another case, case 2. And case 2 is, so if determinant of A is not equal to 0. So then consider the following function. So consider a function phi of E1 En equal determinant, I of V1 up to Vn equals to determinant AV1 up to AVn divided by determinant of A. So we want to show that this is just determinant of vectors V1, Vn. So consider this phi as a function from V power n to f, as in the previous theorem. So and then phi satisfies conditions 1 up to 3. So why this is the case? Again, A is fixed. V1 and Vn are changing vectors. So it satisfies conditions 1 to 3 because let's prove something. So let's prove, for instance, 1. So if we so 1 tells us that, let's prove 1 and let's assume that I equals to 1, and so V1 is equal to V1 prime plus V1 2 prime. And then we know that phi of V1 Vn is the same as determinant of A V1 plus prime plus AV1 2 prime AV2 and so on AVn divided by determinant of A, which is the same as by linearity, by the first property of determinant, AV1 prime up to AVn over determinant of A plus similar thing with determinant of AV1 2 prime AVn over determinant of A, and this is of course this linearity phi of V1 prime V2 and V up to Vn plus phi of V1 2 prime V2 Vn. And similarly, you do it for any other vector, and property 2 is similar because when you exchange two vectors here, then you know that that determinant changes sign, and so phi is also antisymmetric. And finally, if you plug E1 up to En, so 2 is similar, and finally 3 is, if you compute this phi of E1 up to En, that's determinant of A E1, A times E1, A En divided by determinant of A. But this matrix, if you think of it as a matrix, right? This is just a matrix where you take A multiplied by the first vector, and of course you just get the first column of A, second column of A, and so on, nth column of A, so this is just A. And so this is just 1. That's why. And so this function phi equals to the determinant of V1 up to Vn, because by the previous theorem this function is unique. And this proves the claim. So let me erase now probably everything except the claim, and then I will derive the theorem. Okay, we have shown that the claim holds, and this is basically it, because so if we denote the matrix V1 Vn by B, then basically this claim implies that determinant of A times B equals to determinant of A times determinant of B. And that's it. So this is the proof. So again, the main idea is that if you know that determinant of a matrix has this magical properties, that it's the only function satisfying some properties, if you take instead of determinant of a collection of vectors, determinant of some linear map applied to this collection of vectors, then you have to get the same function, except that it can give another value when you plug in bases, and then you will get determinant of A. So when you divide by determinant of A, you get the original determinant, and that implies this theorem. So this theorem has several very important corollaries. So okay, so here is the main corollary. So firstly, let me say computationally corollary. So if you consider determinant of x a x inverse, that of course is the same as determinant of x, determinant of a, determinant of x inverse. So then determinant of x inverse, from this theorem, if you just plug in a b equal to 1, you get 1. So determinant of x inverse is inverse of the determinant. So it means that this is just determinant of x times determinant of a times determinant of x inverse. And these are just numbers, so they commute. So this is determinant of a. And so determinant of a matrix which is similar to A is the same as determinant of A. And then we can give a definition. So definition. So let's suppose we have V to V L, and L is a linear map. So then determinant of L equals to the determinant of M of L, where M of L, sorry, I think I denoted it by M of L, where this M of L is a matrix of L in some basis. So you take a linear map, and then you pick some basis, and you have some matrix, compute a determinant, and call it determinant of a linear map. A priori, depending on which matrix you take and which basis you take, you will get different answers. But because we know that this is how the matrix of a linear map changes when you change the basis, it means that the answer will be essentially the same. So this Y determinant is what's called geometric invariant. It's an invariant of a linear map, not a matrix. And basically this is from where this beautiful theorem follows. And then, of course, from the theorem above, determinant of L composed with M equals determinant of L times determinant of M. So determinant of a linear map, of composition of two linear maps, is a product of determinants. So you can compare it with sign, where the sign of a permutation of composition was the same as sum of signs, and here determinant of a composition of linear maps is a product of determinants. So I think this is very interesting, and of course if you think a little bit about it, you kind of try to understand what is actually intuition behind that and what is the meaning of that, because I mean from the formula for determinants this is a complete magic, right? But here is actually maybe a good intuitive explanation. So suppose L is a map from Rn to Rn, and so linear map, and let's suppose it's an isomorphism. So this means you can think of it as just some way to change coordinates, some transformation of your space to itself. And then for say so what I want to say is that determinant is related to the question how L changes volumes. So let me just say that for some f inside Rn, where this should be a set for which volume can be defined. So defining volume is tricky in higher dimensional spaces, so I'm not going to explain now what that means. Not all subsets have volumes, so there is a complicated theory about that, but you can think of some polytope or some ball or some convex set or something, some shape in a reasonable shape in Rn, and then in Rn there is a way to introduce volumes, and this will be a generalization of volume in R3, and then determinant of L is nothing but it's the volume of L of f divided by volume of f. So determinant tells you how many times the volume changes. If determinant equals to 15, it means all shapes which have volume inside Rn will be 15 times bigger. Sorry, is it correct? Yeah, of course. So that is the meaning of determinant. And if you think about that, then of course the statement becomes obvious, because determinant of L is volume of L of F divided by volume of F, and determinant of M is volume of M of F divided by volume of M. And then of course if you now do L, M and then L, then the volumes first will multiply on determinant of M and then on determinant of L, and that's why the determinant of the composition. So this gives an intuition behind this theorem and behind determinant. So determinant of a collection of vectors, if you just have a bunch of vectors in some space, then you can think of determinant as a volume of a higher dimensional parallelepiped, which is the kind of a span of this vectors. And of course, to make all of this rigorous, we need to talk about volumes, we need to talk about higher dimensional polytopes, and what is a parallelohedron spanned by a bunch of vectors, and so on and so forth. And this is a little bit beyond the scope of this course. But essentially, I want you to remember this mantra that determinants, the geometric meaning of determinant is volume. And in one of the exercises in homework, there was a problem about that in R2, and the same thing holds in all dimensions. So here we finish determinants, and next time we start to talk about eigenvalues, eigenvectors, and characteristic polynomial, which is again a determinant, but this all will be pretty fun, I hope.